one. Alright. Okay, hopefully absolutely the last pre-recorded lecture. Alright. So let's do it. Just get right into it. Alright, so here's what I had planned for class on Wednesday. Specifically just a review, and specifically all of the stuff from Exam 1, so all of the first order differential equation material. So my plan is to go through 1A, B, and 2A, and B from the final review, which, again, check it out. It's posted. Solutions, as of this recording, haven't been fully written yet, but, I'm getting there. Having a week, and I'll tell you more about it in class on Friday. Alright, but anyway, so let's recall what Exam 1 was all about, which was solving first-order differential equations. Alright, so hopefully this looks familiar, because it's the linear equation. Alright, it's first order, only one derivative, and it's linear, right? The only things affecting the unknown function y are addition, scaling, and derivatives with respect to the independent variable x. Okay, alright, so even though there's a multiplication of 2x here, this is still linear. And remember, the secret ingredient to solving a linear equation is to find a integrating factor. Specifically, once your linear equation is in its standard form, which this one is, we slap this up in an integral. That's our integrating factor, and remember, the key ingredient for an integrating factor is that you multiply this into this equation, and the left-hand side turns into a product rule. Alright, and so this is what you end up getting, so let's slowly work for the details here. So you multiply e to the x squared across this equation, so here you'll pick up this times e to the x squared, which is there. This times e to the x squared is guaranteed to be the derivative of e to the x squared times y, and thus e to the x squared y times y is equal to the integral of the right-hand side, which is this stuff. Alright, and now, unfortunately, we gotta integrate. There's just no twos and ways about it with the first order case, just integrals need to be done. This one here, hopefully looks a little familiar, because we definitely either did exactly this one or a similar one. This is always one of my favorite integrals, because it, at first glance, looks like it doesn't work. Right, you look at it, and you got, e to some stuff times some stuff. I always let u be the stuff. But when you first look at it, you're like, well, wait a minute, the derivative of that is 2x, not 2x cubed. And then you go, oh no, it doesn't work. But remember the key rule of chess, which is you see a move and you go, oh, hey, that's the move I do. But then you look at it and you go, oh, wait, no, it doesn't work. But then you go, what if I do it anyway? And indeed, it works. So even though at first glance it looks like u to the x squared does not work here, it actually does, because this can be pulled apart as follows. So the 2x, which is the derivative of this, hey, that's going to turn the du, and x squared, note, is just u, so the integral actually turns into e to the u times u du. Alright, and then that's an integral that, like I said when we encountered it, it's kind of one you just want to have in your head, just because it occurs frequently enough, and if you want to actually go through integrating this, you of course do integration by parts. So our good friend Sunglasses Voodoo for that one, if you let your mind flip back to like week 2 or whenever that was. But right, so this is one you just remember it's e to the x times x minus x, or in this case e to the u times u minus u. And of course do not forget the plus c, right? So, right, one of the more annoying things that happens frequently in this course is, like, when do you include a plus c? And a good rule of thumb is that just at the end is when plus c shows up. Because a lot of the times, a lot of the stuff we've been doing, you've kind of just, like, we never do plus c, right? But you do it at the end here. Alright, and then we divide out by this, which we can because this is non-zero. Before we do that, remember that this involves u's, but we want x's, and u is equal to x squared, so that cleans up like that. And then now we can divide over by this. Now, of course, we could leave it like this as a final answer, because that's an implicit equation. That is a legitimate solution. I just saw that it was not level. It's very annoying, but now it is. So you divide by this, and that would cancel here, and you'd pick up an e to the negative x squared there, and there you go. Y is equal to that, an explicit formula. Hooray. Okay, good times. All right, and there you go. 1A done. All right, now let's talk about 1B. Okay, so 1B, so hopefully you see an equation like this, and the first thing you react to is like, oh, hey, it's an equation in differential form. I bet it's exact, and indeed it is. So remember, to check for exactness is you take the derivative of this with respect to the variable it's not attached to, which is y, and you take the derivative of this with respect to the variable it's not attached to, which is x, and you see that, oh, hey, those partial derivatives line up with each other. And remember, the whole point of this check is that this check guarantees that there is a function f. I need a pause. I'm missing a pause. I spoiled it. Soiled it. Okay. Alright. So the whole point of checking for exactness is that it guarantees that there is a function f that satisfies these two equations right here. And that function f gives us an implicit solution, which we've already spoiled, but we'll get to it. Alright, so anyway, you need to do this check for an exact equation, because if your equation is not exact, then there's no guarantee that you can actually even do this. The exactness guarantees that this can be done. Alright, so in the event, like, oh, I don't know, problem 1 on the final is something like this, you better be demonstrating the exactness before you go in guns blazing with this. Alright. Okay, now when you have this, what do? Alright. I keep trying to highlight and keep shifting it up and down. That's what's going on with that. Anyway. Alright, so when you got this, what do? Well, just integrate with respect to x. So here you'll pick up an x. The integral of sine of x is positive cosine. Is negative cosine, so it makes it positive. That's what I meant. And remember, when you're in here with respect to x, there's a whole ass function with respect to y that would show up, right? So if I take the derivative of this with respect to x, I get this. Right? This does not involve x, so it's derivative in the eyes of x of 0. And a similar story over here, and then now we play the matching game, and I go, alright, this matches that, this matches that, so what does that mean for g of y and g of x? Well, they don't match anything, so they gotta be 0. So that means my f is just x, y cubed, plus y squared cosine of x, and then an implicit solution is given by f is equal to c. Now remember, the reasoning for that is a Calc 3 reason, because this is secretly the differential of something, and the differential equaling 0 means that your function is constant, and so we're looking for the function f to set equal to a constant, and that's why we just go like, oh, now you set equal to c. So remember, we pilfered some stuff from Calc 3 in order to justify why this actually gives you an implicit solution. But, right, I mean, there's an explanation for it, but like what you manually do is just, alright, now I set it equal to c. The end. Right, so the mechanics of it are a little like, yeah, you just do this. But remember, there was a deep reasoning for why that was true. But that's all you do. Alright, now note that this one was kind of easy because f and g don't line up on anything, so there's 0. I bet we're going to see one a little later on in this video where that doesn't happen. Ooh, exciting. Alright, that takes care of 1A and 1B. Alright, so we've seen linear, we've seen exact. Alright, well, what was the other type? Hey, I bet it's this. Alright, so first things first, before we get going, note it's an initial value problem. So we're going to solve, we're going to get an undetermined constant c, and this is going to tell us how to solve for c. Okay. And, be on the lookout for sines and cosines. This is probably a sassier angle than one that I would give you. But, alright. So that is part of kind of this review of Exam 1, is just a lot of like, yeah, remember there's like some integral and some trig shit that can happen, so, you know, just to review that stuff. Alright, well, let's go through reviewing that stuff here by noting that this equation is separable. It is actually also linear, if you wanted to solve it that way, but the right-hand side is equal to 0, and if you've got a linear equation, the right-hand side is 0, it's always separable, so just treat it as separable. But go ahead, be my guest and get an integrating factor. I mean, ultimately, you just kind of do the exact same steps, just kind of in a different order. But anyway, it's separable, so add this over, and then we will separate everything. So we'll get everything involving y on the left-hand side, so the dy and 1 over y. And then dx goes over, and cosine divides over. All right, over here on the left, we have the integral of 1 over y. The integral of 1 over y is log of y. Sine over cosine is tangent, and the integral of tangent, again, that's just one that you should keep in your brain, right? Mathematics is not just memorization, but it's part of the game, and it makes your life a little easier if you just got some of the stuff just at the ready. Okay, but in the event you can't remember this, or you don't remember it, or you don't want to remember it, note that the integral of tangent, this is sine over cosine. This is just a u substitution, right? Let u equal cosine, and the derivative of cosine, of course, is minus sine, so this turns into the integral of negative 1 over u, so it gives you negative log of u, or negative log of cosine of x. Don't forget the plus c. Alright, and then now, remember what we do here. When you've got log of y is equal to some junk, it's going to be c times e to this stuff. But e to the negative log of something is just 1 over that something, so we pick up y is equal to c over cosine. And if you were to pop this into, like, oh, I don't know, Wolfram Alpha or something, you actually get y is equal to c secant, but there's no reason to convert it over to secant. We're going to be plugging in a value here, so, like, if all we wanted to do was just solve this without this, like, maybe I would say write it as c times secant. It just looks a little better. But I'm plugging in this, and it's easier to plug that in the cosine, so let's do that. Alright, and there we go. Okay, so plug in the initial condition. Now, like I said, this is a spicier angle than any one that I would give you, but right, so it's pi over 6, it's 7 pi over 6. Think about where that lives. That's in the first, second, third quadrant, right? It's past pi. Alright, and specifically it's pi over 6 past it. And that gives you your right triangle, and that gives you then what you're looking for. So really you're just trying to figure out what cosine of pi over 6 is, which is root 3 over 2. But note, it's negative in this case because we're hanging out in the third quadrant, where only tangent is positive. Right. Cosine, again, remember, is the x-coordinate. So if you think about that triangle in your mind's eye, living in the third quadrant, its base, which is cosine, is technically a negative number. Alright, and of course it's equal to negative 3, so just multiply this over. Root 3 times root 3 gives me 3, negative times negative gives me positive, and the 1/2 just hangs out in the bottom, and so c is 3/2, and there you go. Pretty reasonable looking answer. And that's it. That's the story. Man. Alright, yeah, so this is basically just a veiled warning of brush up on some trig. Right, just be mindful of some integrals and derivatives involving trigs and some basic trig values. So knowing how to evaluate sine and cosine and tangent at pi over 3, pi over 4, pi over 6, and any multiples thereof that live in the first, second, third, and fourth quadrant. Okay. Like I said, on the final, if there is one, which I don't know, I didn't write the exam or anything. Yeah, it wouldn't be 7. It'd be something like pi over 3. It'd be, yeah. Or maybe I'm lying. Maybe there's no trig at all. Oh my god. Who knows? You can't know what I'm doing if I don't know what I'm doing. I don't know. Shit, more trig. Let's go. Alright. Alright, and so here we go. Here is to be, and not to be. Let's finish it up. Okay, so, yeah, so that takes care of pretty much anything from exam 1 that I'm going to throw at you. So, yeah, just be prepared for linear, separable, and or exact, and you'll be good to go. Note, I'm not going to subject you to any word problems. I already did that to you on an exam. We're good. I don't need to do it again. So, there we go. Alright. Yo. Alright, so again, it's in differential form, which means it's probably exact. And again, with the pauses, I'm missing the pauses. The pauses, man, I don't have them. Where are they? Ba-bang. Come on, load up. There you go. Alright, so again, this is exact. Take the partial of this with respect to y, the partial with respect to x, we get this. Now note, this guarantees that there is an f that satisfies the equations we want. Specifically, the partial of f with respect to x is equal to this stuff up here. The partial of f with respect to this stuff is equal to this stuff up here. Then we integrate with respect to x, integrate with respect to y, and we play the matching game. So my x squared Well, it's got to match my h of x. The cosine x sine of x, that matches that piece right there. My g of y matches my tangent of y. Yay! So that gives me my f, that gives me my g of y, that gives me h of x, that tells me what f is equal to. It's this beautiful function right here. X squared plus cosine of x times sine of y plus tangent of y. Beautiful. Alright. So, hey, we've got our f, which means that we can now get our implicit solution. But remember, I have an initial value to plug in, so be careful. There are initial value problems on this exam. Don't be the doofus that forgets to plug them in and loses, like, you know, a third of the points. Like what happened on exam 3. Yeah. Don't be that person. It'd be awful. Alright, so we're not going to forget to plug in the initial conditions, so let's go ahead and do that and finish things off for this conversation for today. Alright, okay, so an implicit solution is given now by setting that equal to c. Now remember your initial condition is y of 0 is equal to pi over 4. Alright. And plugging that in, so note this is my x, that is my y, so be careful, especially with exact equations and initial conditions, that you plug everything in the right spot. So x is 0, sine is pi over 4, so that zeroes out. Cosine of 0 is 1, sine of pi over 4 is root 2 over 2, and tangent of pi over 4 is 1, pi over 4 being the spot where sine and cosine line up with each other. Alright, it gives me my c, and that's it. We're done, yay! Alright, and that covers everything from exam 1 that I will throw at you. There we go. Alright, so that's primarily what I had planned for class on Wednesday, and time permitting I would have done, started to get into the material from exam 2, but that's what we'll do when you see me Friday. Okay, alright, with that, that's it. Last pre-recorded lecture of the semester. Hooray. Okay. Well, I'll see you next time for some more review.